Welcome to another video of Optatube. Today we are cracking open the engine room of the modern power grid to get our heads around a really cool concept called economic dispatch. So, have you ever really thought about how the lights stay on? How it's always there and always affordable, even when the sun goes behind a cloud or the wind stops blowing? Well, it is definitely not magic. It's this super complex, high-stakes balancing act. And the number one rule is this. For every single second of every day, the amount of electricity being made has to perfectly match the amount being used. No more, no less. So today, we're going to build a simple model to see exactly how it all works. Okay, so to understand the solution, we first need to meet the two main players in our simplified little power system. Think of it as the old guard on one side and the new kid on the block on the other. What we're looking at here is a classic trade-off. Our thermal plant, think coal or natural gas, is totally controllable. We can tell it to ramp up or down whenever we need, but that fuel costs money. Our solar plants, on the other hand, well, its fuel is sunlight, which is free. The catch? You can't just ask for more power at 9 o'clock at night. It's completely at the mercy of the weather and the time of day. Now, don't get too hung up on the math here. The cost to run our thermal plant isn't just a straight line. The main thing you need to know is that as you ask for more and more power from it, the cost for each extra megawatt actually goes up. It's kind of like your car's fuel economy. It gets worse when you're flooring it at really high speeds. Same idea here. The generator gets less efficient when it's running flat out. The solar plant's output is a whole different story. It's way more predictable, but it's also way more rigid. We can pretty much model it as a simple wave, right? It starts at 0 at midnight, smoothly climbs to a peak around noon when the sun is directly overhead, and then falls right back down to 0 by sunset. It's this beautiful, natural rhythm, but it's a rhythm we have to work with, not command. And finally, there's us. The demand for electricity, what we call the load. It follows its own daily rhythm too. It's pretty low in the middle of the night. Then, bam, it spikes in the morning as everyone wakes up and businesses get going. It might dip a bit midday, and then it usually peaks again in the evening when we all get home, flip on the lights, and start making dinner. These two patterns, solar supply and our demand, are the waves our grid operator has to surf every single day. So we've got our players, and we know the demand we have to meet. The name of the game now is optimization. The goal is to figure out the absolute cheapest way to run this whole system for a full 24 hours, all while playing by some very, very strict rules. And this slide, well, it boils the entire problem down to just 3 simple points. First, the objective. Spend as little money as you possibly can. Second, the golden rule, the most important one. What you generate must equal what's being used at every single moment. Solar plus thermal has to perfectly match the load. And third, a simple law of physics. You can't get more power out of the solar farm than the sun is giving it. Simple as that. All right, the stage is set. We've got our rules, we've got our players. Now let's run the numbers and see what the cheapest, most efficient 24-hour schedule actually looks like. Let's do this. And there we go. Our model has crunched all the numbers and found the sweet spot. It's figured out the perfect minute-by-minute schedule for our thermal plant that's going to save us the most money over the entire day. Let's look at the play-by-play for a few key moments. So, at 3 a.m., deep in the night, demand is low at 110 megawatts. There's no sun, so the thermal plant is doing all the heavy lifting. But now, check out what happens at noon. Demand is a bit higher at 120 megawatts, but the solar plant is pumping out its maximum 50 megawatts for free. This lets the thermal plant power down to just 70 megawatts, which saves a ton of money. Then, fast forward to the evening peak at 8 p.m., demand is at its highest, solar is back to 0, and the thermal plant is working hard again to supply all 130 megawatts. So what does this look like over the whole day? When we add up all the energy produced over the full 24 hours, you can see the thermal plant did provide the majority, about 74%, making sure the light stayed on day and night. But our solar plant pulled its weight, carving out a really significant 26%, providing all that clean, free energy during the sunniest parts of the day. And here it is, the bottom line. All that complex math comes down to this single number. The total cost to power our little virtual city for one day is just over 28,000 euros. Now, to see why that matters, think about this. If we had run the city for the whole day using only the thermal plant, the cost would have been closer to 35,000 euros. That is the real, tangible result of smart economic dispatch. Using that solar saved us almost 7,000 euros in a single day. You might be thinking, okay, that's a neat little simulation, but what's the big deal? Well, the logic we've just walked through is incredibly important. It's a super simplified version of what grid operators do every single day, and it's basically the blueprint for how we build a cleaner, more efficient, and more affordable energy future. So let's just recap the core logic here, because it's pretty simple, really. First, the goal is always to keep costs as low as possible. Second, you do that by using the free renewable energy, our sun, anytime you can get it. Third, you use your controllable thermal plants to fill in all the remaining gaps and make absolutely sure demand is always met. This fundamental logic is what scales up from our little two-plant model to managing an entire country's power grid. And that brings us to our final thought. We've seen how this works with just two players, but the modern grid, it's getting way more complex. What happens when you add wind power, which has a totally different pattern than solar? What about massive batteries that can soak up that cheap midday solar power and save it for the evening? The game gets more complicated for sure, but the goal stays exactly the same: reliable, affordable, and cleaner power. So if you are interested in the energy market and power system modeling, and you want updates and insights about the global energy market, be sure to follow the Optatube channel. Thanks for watching.